Okay, so today we're looking at another application of derivatives, and we're looking at related rates. So a related rate problem would be one where our two variables have some sort of relationship between each other. When we're looking at related rate problems, you're going to be, first of all, given a rate of change of one or more quantities, and you're going to be asked to solve for a different rate of change for another quantity. So here, before we get into some examples, we're going to go through some of the basic steps for solving rates. Now, fair warning, this video is a little bit longer than some of the others. I'm going to try to give you as many examples as I can. I also expect that we're probably going to need a couple of these to go through the practice problems. So you might choose to watch a section of the video, go and do some of the practice questions, watch a section of the video, and so on. There's also going to be a couple times in here where I ask you to pause the video and try some of the questions on your own beforehand. So when we get into solving related rate problems, the first thing you're going to do is read through the problem and figure out what you're given and what you're looking for. And so you're going to state the given rate of change, and you're going to state the rate of change that you're looking for. And because we're going to be using implicit differentiation throughout, you want to make sure you're using Leibniz notation. So that's like your dr, dt, dx, dt, and so on. Once you know what you have and you know what you're looking for, you have to figure out a formula that you can use to solve in the context of the question. Now, sometimes there are formulas that you already know, like the volume of a cylinder or volume of a cone. Sometimes they're given to you in the context of the question, and then other times you have to derive your own formula. For example, we're going to get into questions where we're looking at relation related to motion, and you might have to look at similar triangles, you might have to look at Pythagorean theorem, and so on. What's important for you to know is that the formulas that you come up with can only have the variables from the numerators of the given and unknown rates of change. So for example, if I was looking at the volume of a cylinder, volume equals pi r squared times height, and the question that I was looking at related to the rate of change for volume and the rate of change for radius, I would have to rewrite my formula so that h was written in terms of radius. Once we have our formula, we take the derivative of the formula with respect to time, we sub in what we know, and then we solve for what we don't. Okay, so those are the basic starter points. It's important to know on the bottom, unless you're stated otherwise, you should have your answer in simplified exact values. So try to avoid decimals. And as well, make sure that you have the correct units. So if it's velocity, you're going to have like meters per second. If it's volume, the rate of change for volume, it might be centimeters cubed per minute, and so on. All right, so let's hop into some of the examples. First of all, we're going to look at some rate problems related to area and volume, and then we'll get into some motion problems. So example number one, a spherical balloon is expanding, and the rate of increase of its radius is 10 centimeters per minute. And the question says, at what rate is the volume increasing when the radius is 10 centimeters? So we look at first what we're talking about. We're talking about a spherical balloon, so we're talking about a sphere. Okay? And so a sphere is going to have a radius. We're talking about volume. So volume of a sphere. Volume of a sphere is 4/3 pi r cubed. And we look at what we're given in the formula. So we're told that the rate of increase of the radius is 10 centimeters per minute. So we're given that the rate of radius with respect to time is 10 centimeters per minute. And we're asked at what rate is the volume increasing when the radius is 10 centimeters. So we're being asked for the rate of volume. So we're asked to find dV dt when the radius is 10 centimeters. Make sure you don't mix up the rate of 10 centimeters per minute is different than the radius, the instantaneous radius at 10 centimeters. All right, so we have the volume of the sphere is 4/3 pi r cubed. We have what we're given, the rate that we're given, and the rate that we're looking for. So our next step is to take the derivative. And so the derivative, if we're given the formula for volume, is 4/3 pi r cubed. The derivative of that is going to be 4/3 pi ddt of r cubed. So 4/3 pi times 3r squared dr dt. Again, remember we're using implicit differentiation here. Now, before we go any further, it's important that we simplify as we go. So I have dv dt equals 4/3 times 3 leaves me with 4 pi r squared dr dt. Once we have our derivative simplified, then we're going to sub in the values that we know and any other values that, so we'll sub in the rate of change that we know and then any other values that we know as well. So we're looking for, we've got dv dt equals 4 pi r squared and dr dt. Well, we know that dr dt from above is 10 centimeters. So we're going to sub that in. 4 pi r squared times 10, which gives us 40 pi r squared. Once we have that, then we can look for the specific value that we're given. So dv dt at the point when the radius is 10. And so 40 pi times 10 squared leaves us with 4,000 pi. And our units, we're talking about volume changing with respect to time. Our radius was in centimeters, so our volume is going to be centimeters cubed per minute. Again, at any point, if I go too quickly, just pause, rewind, look at the example, and then move on to the next one. So example number 2, we're looking at a sphere again. You're inflating a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. And the question is, how fast is the radius increasing when the diameter is 50 centimeters? So again, we're given our sphere with our radius. We're given, it says you're inflating the spherical balloon so that the volume is increasing at a rate of 100 centimeters cubed per second. So we're given the rate of volume with respect to time. So dv dt is 100 centimeters cubed per second. Sometimes the units might help you in determining which one we know and which one we're looking for. Then the question says, how fast is the radius increasing? So we're looking for dr dt at the time when our diameter is 50 centimeters, meaning our radius is 25 centimeters. So again, we're talking about volume, so we're going to be doing volume of a sphere is 4/3 pi r cubed. We take the derivative, and looking at our last question, I'll shortcut this one a little bit. We just did this in the last question. We've got 4 pi r squared dr dt. Once we have our derivative, then we're going to sub in what we know. We know that the radius is 25. We know that the dv dt is 100. So we've got 100 equals 4 pi times 25 squared. And we're looking for the rate of change for the radius. So simplifying, we've got 100 equals 2500 pi, again, keeping things exact, dr dt. Divide everything by 2500 pi. And if we put that in simplest form, we've got 1 over 25 pi equals dr dt. So the rate of change for the radius with respect to time is 1 over 25 pi centimeters per second. Okay, switching shapes, the next one we're going to be looking at the shape of a cylinder. So a water tank has the shape of a cylinder, and the tank is filling at a rate of 2.3 meters cubed per minute. If the tank has a radius of 3 meters, we want to know at what rate the water level is increasing when the water is 4.1 meters deep. So it sometimes helps to have a visual. We've got our cylindrical tank. We've got some level of water. We've got our radius. And we've got the height of the cylinder. Now, if we look in the question, we're told the tank is filling at a rate of 2.3 meters cubed per minute. So this is going to be our volume. So we're given dV dt, and we're told that that's 2.3 meters cubed per minute. We're also given that the radius equals 3 meters. And then the question says, at what rate is the water level increasing when the water is 4.1 meters deep? So we're being asked to find dH dt when the height is 4.1 meters. Now we're talking about the volume of a cylinder. So volume of a cylinder is pi r squared times height. And the first step we have after that, or the next step we have, is to take our derivative. So dV dt is pi r squared times height. Now actually, before we do that, let's sub in what we know. We know that the radius is 3 meters, so we can sub that into our formula. So that would make our volume pi times 3 squared times the height. So volume would be 9 pi times the height. Makes it a little bit simpler when we're doing our derivative. So volume equals 9 pi times height. We can't have the radius in there because we're dealing with just velocity and height. And as I said before on that first page, our formula has to only include the numerators from those rates of change. So we've got volume of the cylinder is 9h, or 9 pi h. If we take the derivative, that's going to leave us with 9 pi. The derivative of h is just 1, dH dt. So that gives us 9 pi dH dt. At this point, we're as simplified as we can be, but we can sub in what we know. We know that the derivative of velocity with respect to time is 2.3, and that equals 9 pi dH dt. We can divide by 9 pi. Now, when we're dealing with fractions, we don't want to have any decimals in the fraction, so when we put 2.3 over 9 as a fraction, a proper fraction in lowest terms, we get 23 over 90 pi equals dH dt. There's no variables to sub into, so we're done the question. And we have that the change in height with respect to time is 23 over 90 pi meters per minute. Again, always double check your units. Now it's your turn. I want you to take a look at the question, pause the video, try it on your own, and then come back. All right, so looking at this question, we're talking about a circle, and we're talking about the area of the circles, the area of the circle changing at a rate of negative 15 centimeters squared per second. So our radius, area, A is area, R is radius. We're also talking about circumference in here, so we're going to have to look at our circumference formula. First of all, look at what we're given. We're given that the change in area with respect to time is negative 15 centimeters squared per second. And we're being asked to find the rate of change for the radius. So we're being asked to find dr dt. And we're asked to find that when the circumference equals 90 centimeters. Well, circumference is not one of my numerators, so I'm going to have to do some rearranging of a formula. Circumference is 2 pi r. Now, circumference is also pi times diameter, but we don't want to deal with diameter, we want radius, so I'm using 2 pi r. Circumference, we're told, is 90, and we've got 2 pi r. We can divide by 2 pi, and 90 divided by 2 is 45, so we're left with the radius being 45 all over pi. Now we can come back to our circle, and we're talking about area and radius. So we know that the change in area with respect to time is negative 15 centimeters squared. So we're going to start off with the area of a circle. The area of a circle is pi r squared. So we take our derivative. We get 2 pi r dr dt. We've already solved for r, so we can sub that in. We also know that the change in area with respect to time is negative 15. So you got negative 15 equals 2 pi times 45 over pi dr dt. Doing a little simplifying, we've got negative 15 equals 90 dr dt. And rearranging, we divide by 90, we get dr dt equals negative 1/6 centimeters per second. All right, we'll look at one more example for volume, and after that you may choose to take a break from the video, try some of the questions, or pause the video, come to class tomorrow, do some of the practice questions, and then watch the rest of the video later on tomorrow night. Our last example involves a cone, but we're also going to be looking at similar triangles. So water is draining from a cone-shaped tank at a rate of 2.5 meters cubed per minute. So we've got our cone, and we've got water that's at one particular level, and it's draining. So it's going to get less and less as we go. So our original radius is 2.5 meters, and the original height of the cone is 8 meters. When we look at what we're given the rate of volume changing. So derivative of volume with respect to time is negative 2.5 meters cubed per minute. And we're being asked at what rate the water level is dropping. So I'm choosing to use that as h. So we're asked to find the change in height with respect to time. If you'd wanted to use the change in depth with respect to time, that's fine. It's just that in our cone formula, I usually use h. And so we're asking for that when the height is 2.8. So if we look at the formula for the volume of a cone, we have 1/3 pi r squared times height. And here's a problem. Our question has velocity and height, and our formula has an r. So we're going to have to come up with a new formula or derive a formula that only uses height and volume. And so we're going to have to find a way to represent the radius using h. And this is where some similar triangles are going to come in. So before I continue with the question, I'm just going to do a real quick recap of similar triangles. If I have a triangle that's x by 12 and a triangle that's 3 by 4. Similar triangles means that the triangles maintain the same proportion. So x to 3 would be the same as 12 to 4. And so x over 3 is equal to 12 over 4. And if I were to rearrange and solve this, I'd have 4x equals 36 and x equals 9. Because these are proportional, I could have also written this as x over 12 equals 3 over 4, and I'd get the same solution. So if we are working with similar triangles, we're looking at common proportions or equal proportions. And so that relates to what we're going to be talking about here. We have this cone. We start with a radius of 2.5 and a height of 8. But as the water goes down, we're going to have the same proportion, but just less as we go. And so the radius is still going to be the radius, and the proportion between the radius and the height is still going to be the same. So because these are similar triangles, we can say that the radius over the height is the same as 2.5 over 8. And we can use that to then rearrange and write this equation in terms of r. So solving here, we'd have r equals 2.5 times height divided by 8. Again, we don't want decimals in our fraction, so that would reduce to 5h over 16. Now that we have our formula, or we have a relationship between our r and our h, we can go back to our original formula. So the volume of the cone was 1/3 times pi. Instead of r, though, we're going to write 5h over 16 squared times h. And we'll simplify before we take the derivative. So simplifying, that gives me 1/3 times 5/16 squared gives me 25 over 768. And we've got a pi, and h squared times h gives me h cubed. So this is the volume, and from there I'm going to take my derivative. So dv dt, the 3 is going to come forward and multiply by that 25 over 768, That's going to give me 25 over 256 times pi times h squared. And don't forget the dH dt again, because we're doing implicit differentiation. At this point, we can sub in what we know. So we have negative 2.5 equals 25 over 256 pi. H, we know, is 2.8 squared dH dt. When it comes to solving, we're going to take that negative 2.5, we're going to divide by the 25 over 256, we're going to divide by the 2.8 squared, we're going to divide by the pi, and it's going to leave me with negative 160 over 49 pi. My units would be meters per minute, and that's going to be equal to my change in height with respect to time. So again, in terms of how I solved that, I divided by 2.8 squared, I divided by the pi, and I divided by the 25 over 256. You can certainly simplify the 25 over 256 and the 2.8 squared, and then take negative 2.5, divide by that number. But remember, you're also dividing by pi, and we want to keep our answers exact. So again, at this point, you might choose to pause the video, do some of the volume and area questions, and then come back to these tomorrow to look at related motion. All right, so looking at some related motion questions here, these are all going to be ones that involve triangles. So we're going to be looking at similar triangles or Pythagorean theorem. So the first example here, it says a spotlight on the ground shines on a wall 10 meters away. A man 2 meters tall walks from the spotlight towards the wall at a speed of 1.2 meters per second. And the question is, how fast is his shadow on the wall decreasing when he is 3 meters away from the wall? Any of these questions, it's important that you draw a diagram so you can get a visual of what you're working with. So we've got our wall, we've got this spotlight and it's shining up on the wall. And then we've got our little man here, he's 2 meters tall. And he's casting a shadow. So we're going to have the height of the shadow here. And we have the distance between the spotlight and the wall is 10 meters. And we're going to let S equal the distance walked from the light. So that would be S here. And if his distance from the light is S, then as he's approaching the wall, this would be 10 minus S. That's going to come into play here shortly. Now, if we look at what we're given, we're told that the man is walking towards the wall at a speed of 1.2 meters per second. So we're given his distance with respect to time is 1.2 meters per second. And we're being asked, how is his height changing? And so how is the height changing with respect to time if S equals 7 meters? So we're told that he is 3 meters from the wall. But since we let S represent the distance he's walked from the spotlight, if he's 3 meters from the wall, that means he's actually walked 7 meters from the spotlight. So we need to put our question in terms of H and S because those are our numerators in this case. So we're going to look at similar triangles because as this guy is approaching that wall, his shadow is going to get bigger and bigger and bigger. So looking at a triangle here, we know that this was S, and we know that the entire length was 10, so this was 10 minus S. Let me redraw that there. We know the entire length of this triangle is 10, and we know that this portion of the triangle is S. We know that the height of the man is 2, and we know that the height of the shadow is H. So setting up a proportion, we can say that the height over 10 is equal to 2 over S. We want to put everything in terms of height. So 2 times 10 is 20, and H is going to equal 20 divided by S, or we could write that as 20 times s to the negative 1, which will be more helpful when we're doing our derivative. So now we could have put this in terms of s as well and solved it, would have still got the same answer. So dh dt would be negative 20s to the negative 2 ds dt. At this point, we sub in what we know. dh dt equals negative 20, I'm just going to move this to the bottom, over s squared, and we know that ds dt is 1.2. Now, since this was given to me as a decimal, I'm going to keep it in decimal format, but my final answer I'll convert to exact. So dh dt, negative 20 times 1.2 is 24, so negative 24 over s squared. We're told that s is 7, so we can sub in that information. So dh dt, when s is equal to 7, is negative 24 all over 7 squared, which is negative 24 all over 49. And we're talking about the change in height with respect to time is meters per second. Okay, so another common related rate problem that we'll see in terms of motion has to do with vehicles traveling. And so when we're talking about vehicles traveling, you're often going to see things expressed as north, south, east, and west. And so we're using the Cartesian plane, but we're still going to relate it to x's and y's. So we've got north, south, west, and east. Okay. So we're told car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for the same intersection. And the question says, at what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So we have one car here. Car A is traveling west. So traveling westbound means they're going from east to west. And that means they're on the x-axis. So we're going to let that represent x. And then car B is traveling north at 60 miles per hour. So they're traveling on the y-axis. So we're going to use y. Now, both are headed towards each other, so the distance between them is decreasing, so I'm going to use negatives. We're told that car A is traveling west at 50 miles per hour. Car A is x, so dx dt is negative 50 miles per hour. And car Y, or car B, is headed to that intersection at a rate of 60 miles per hour. So dy dt is negative 60 miles per hour. Okay. And we're being asked at what rate are the two approaching each other. So we're really looking at that hypotenuse, because as they get closer and closer to each other, that distance is going to decrease. We're going to call that hypotenuse z. Okay. So we're looking for dz dt. So I'm going to draw a separate triangle here. We know that at this point here, we start at 0.3 miles, and here we start at 0.4 miles. Again, our 0.3 is x and our 0.4 is y. We need to figure out what z is. And so we're going to be using Pythagorean theorem. So this relates to a squared plus b squared equals c squared. So during this question, z is going to be the square root of 0.3 squared plus 0.4 squared. And so z is going to be 0.5. Now we take that formula, x squared plus y squared plus z squared. Equals z squared. And that's going to be our initial formula. We're going to take the derivative. Again, we're doing implicit differentiation. So we're going to have 2x dx dt plus 2y dy dt equals 2z dz dt. We sub in what we know. So we know the 2, we know x is 0.3, we know the rate of change is negative 50. For car B, we've got 2 times 0.4, rate of change is 60, and then our z is 2 times 0.5 dz dt. Lots of simplifying here. We end up with negative 30 minus 48 equals dz dt, because 2 times 0.5 is 1. And so one last step of simplifying, we end up with negative 78 miles per hour equals dz dt. So as those cars are approaching at those rates, as they're approaching at that rate, they're actually approaching each other at 78 miles per hour. All right, so we'll do another Pythagorean theorem question. A man starts walking north at 1.5 meters per second, and a woman walks west from the same point at 2 meters per second. So here they're starting at the same point, and they're walking away from each other. So man starts walking north at 1.5 meters per second, so that's going to be y. And woman starts walking west at 2 meters per second, and that'll be our x. As they're walking away from each other, their distance is increasing, so I'm going to make my derivatives positive. Some of you might be thinking in terms of physics and having things be positive direction and negative direction. So I'm hoping that you're not confusing the two as I'm explaining them. So we're told a man starts walking north at 1.5 meters per second. North, we've said, is y, so dy dt is 1.5 meters per second. And then dx dt is 2.0 meters per second. I'm just going to write it as 2 meters per second. We're also asked the rate of the distance increasing between them 1 minute later. But our units are in seconds, so this would be 60 seconds. And again, if you think about what we just did in the last question here, this would be our z here. So we're looking for dz dt at the time when time is 60 seconds. So in order to solve the question, we need to figure out where the points are at 60 seconds. So when t equals 60 seconds, x will be 60 times 2, which is 120 meters away. And y will be 1.5 times 60, which is 90 meters away. So doing Pythagorean theorem, z will equal the square root of 120 squared plus 90 squared, which is 150 meters. We take that formula, x squared plus y squared equals z squared, and we do the derivative. So 2x dx dt plus 2y dy dt equals 2z dz dt. Sub in what we know. 2 times 120 times 2 plus 2 times 90 times 1.5 equals 2 times 150 dz dt. Again, lots of simplifying. 480 plus 270 equals 300 dz dt. 480 plus 270 is 750 equals 300 dz dt. And when we divide, we get 2.5 meters per second. Now we can also express that exact, which would be 502 meters per second. I left it in decimal in this case just because it's a little bit more visual to understand. All right, just a couple more examples here. Again, we're still talking about rate of change. We've got a ladder, a 10-meter long ladder that's resting against a vertical wall. The bottom of the ladder starts sliding away from the wall at a rate of 1 meter per second. The question is, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 meters away from the wall? I'm sure you've all looked at a ladder and wondered, how fast is it dropping at certain points? All right, so we've got the height. We know that the ladder itself is 10 meters long, and x. Sorry, my smartboard's acting up today with all these little squigglies. So we look at what we're given. We're given that the distance the distance it's moving away from the wall, so dx dt, is 1 meter per second. And we're asked to find how the height is changing with respect to time. And we're asked to do that when x equals 6. So again, in order to do this question, we have to figure out what are the values when x equals 6. So when x equals 6, our h would be the square root of 10 squared minus 6 squared, which would be 8 meters. Again, this is a Pythagorean theorem question, just using different variables. X squared plus h squared equals 10 squared, which is 100. So x squared plus h squared is 100. Take our derivative, 2x dx dt plus 2h dh dt equals, remember the derivative of 100 is 0. We sub in what we know. 2 times x times the 1 plus 2 times h dh dt. Now, absolutely, you could sub in the rest of the values here. I'm just showing you a different way to go about doing it. So we have 2x plus 2h dh dt equals 0. If you would ask for just the rate of change and not been given a specific amount, then this is what you would do instead of subbing everything in. And so if I wanted to get dh dt by itself, I would first subtract 2x, so I'd have negative 2x. Then I divide by 2h, which would reduce to negative x over h. So the derivative of height with respect to time when x equals 6, and we found out that that also means h is 8, would be negative 6 over 8, which is negative 3 over 4 meters per second. So again, we could have subbed in the negative 6. We could have subbed in the negative 6 here and the positive 8 here and done this in one step. I just chose to show you a different method. All right, one final question. I'll get you to pause the video, try this one on your own, and then come back and check your answers. So this question is similar to the two people walking away from each other. We've got our Cartesian plane. We're just going in different directions this time. They're starting at the same point, and one goes south and one goes west. And again, as they're moving, their distances between each other, or the distance between each other, is increasing. So they're close and then further and further and further away. So we have our rates that we're given. We're given x and y. And so dy dt relates to south. So south is 60 kilometers per hour. And then dx dt is our west, and that's 25 kilometers per hour. So we have to figure out 2 hours later where these vehicles are. So 2 hours later, x would be at 25 times 2, which is 50 kilometers away from that origin. And y would be 60 times 2, which is 120 kilometers from the origin. We can then figure out how far away they are from each other. So z is going to equal 50 squared plus 120 squared, all square rooted, which is 130 kilometers. Take our Pythagorean theorem, x squared plus y squared equals z squared. And the derivative is going to give us our rate of change. So 2x dx dt plus 2y dy dt equals 2z dz dt. We sub in what we know. 2 times 50 times 25 plus 2 times 120 times 60 equals 2 times 130 dz dt. Again, lots of simplifying. 2,500 plus 14,400 equals 260 dz dt. 16,900 equals 260 dz dt. And when we divide, we get dz dt when time is 2 hours is 65 kilometers per hour. And that's it. So hopefully I've given you enough examples that you have a good idea where to go. I know that there's still going to be some examples in the textbook where you're going to have to derive some formulas. There's a couple that involve equilateral triangles and having to figure out a formula from there. But I'm going to be giving you a couple days to work on some of the practice questions. Thanks for bearing with me and listening to me talk. Hopefully you at least took a few breaks in between. And I look forward to talking to you in class and helping you with any questions that you have. All right, guys, have a great night, and we'll see you tomorrow.